All right, hello and good morning. Let's talk about our next lecture topic, which we're going to look at Chapter 4 and 5 in Tidy Modeling with R, as well as Chapter 5 in Introduction to Statistical Learning with R. So, we have two textbooks, and the two textbooks are a little bit different from each other. They have different aims and different goals. We're going to be working through tidy modeling with R, which will give us kind of this very practical, hands-on application as far as working actually through a data set. And the data set that we're going to be working through is the Ames housing data. Okay, and so let's go ahead and take a look at that. So Ames is a city in Iowa, and we have some data on kind of houses and stuff from 2006 to 2010. So this is, I guess, 14 to 18 years ago, and the housing market was quite a bit different. Even just going back 14 to 18 years or so. But we have information on, close to 3,000 different houses and stuff, and we have information like how many bedrooms there were, and what is there a garage, and the size of things like that. We have information on the location, the neighborhood it's in, some information about the lot, information about the condition and quality of the house. Are there nice, is the roof in good condition and stuff like that. And then finally, what was the sale price of the house? And this is going to be kind of the variable that we want to predict based on the other things, right? So it's kind of like, if I show you a house and it's this big and it's in this neighborhood, can we predict how much the house is going to sell for? Okay. The authors have already done some cleanup of the data, and we'll take a look. So we can load this data up in R. So you might need to have so anytime you see a call for library and then you try to do that, if it doesn't work, you probably have to install that package. So I'm going to go ahead. I'm going to just follow along here. We're going to load up library model data, and then if we do that, we can call data Ames, and then let's just take a look at Ames. So we see we have 2,930 rows, 74 variables, and let me expand on this, and let me also click this, and we'll look at the viewer. And we have stuff like this: 1-story 1946 and newer, all styles; 2-story 1946 and newer; 1-story PUD, I don't know what that is. Split for, I guess this is just kind of like the subclass, the zoning: residential low density, residential medium density, residential high density; lot frontage, lot area, the street, is it paved, is there an alley? Apparently not for these ones. The shape of the lot, slightly irregular or regular; land contour, the utilities. Let's see, some of these things we can filter. Okay, so this one might be like, so no sewer, no, I don't know what that is, something. These are some of the options for lot configuration: land slope, gentle, moderate, severe, neighborhood, and there's several different neighborhoods. Condition, I don't know what these things mean. 1 family, 2 family, duplex, townhouse, things like that. These are the different story house styles. Overall condition, and it can have a house in excellent condition, average condition, very poor condition. When was the house built? Ooh, some were built as early as 1870, some as late as 2010. Was year it was remodeled or an addition was made. The roof style, all kinds of stuff, right? There's 74 of these variables. Some of the bigger ones are important ones. Well, this is basement square footage. And total basement square footage. So how, if your house has a basement. This is ground living area. This is basically how big the house is. So, you know, you see a lot of houses around 1,000 square feet, 1,800 square feet, so on and so forth. And, you know, different kinds of stuff here. All right, so this is, that's the Ames housing data. And so we can look at one of the variables, which is going to be the sale price of the house. Okay, we need to kind of load up tidy models in here. So we will we'll call library tidy models. All right, and then tidy models has certain functions. And actually, I had loaded tidy models earlier. Normally, if you load tidy models for the first time, like a bunch of information appears about all the different packages it loaded. And tidy models has some functions that actually have names that appear in other packages as well. And so a command that you should run is called tidy models prefer. Okay, and what this is going to do is it's going to kind of resolve any kind of conflicts. So that if there's if you name a function that appears in other places, it's going to use the tidy models version of that function. And the first thing that we want to do is, and I'm not going to bother typing out this code here, or I guess I can just copy and paste it, is we're going to create a plot using ggplot. And it's going to be a histogram of the sale price of the house. Okay, so if you look at if we open up Ames, one of these things should be sale price, I think. Looking for it. Oh, I think I have to go all the way to the end. The 72nd column is sale price. Okay, and so, you know, this whole house sold for $215,000. There's a house that sold for $105,000, $195,500, and so on and so forth. And we can create a plot of this thing. And so this is our histogram of sale price. And we can see, okay, so down here would be houses that sold for 0, and we don't have very many. This is houses that sold for 200,000. This line right here is 100,000. So we see a lot of houses sold between 100 and 200,000. Some houses sold for, you know, 400,000, and you know, only a very few sold more than 400,000, $600,000, and I guess there was a house somewhere, $800,000. You know, I might be able to look at this and just sort. So the cheapest one was $12,789. That was an abnormal sale condition, so probably something something unusual about this house. Maybe somebody died and they were just trying to get rid of something. Okay, the most expensive house that was sold was $755,000, which will probably get you today a small house in Los Angeles, but in 2006 to 2010, it was the most expensive house sold in Ames, Iowa, at least in this data set here. But anyway, we can plot that, and this is kind of what the histogram looks like. And so, you know, we have this long kind of tail. I mean, there's not very many, but it's enough to kind of put on some skew to our graph. So we might want to make some adjustments, because it is when you have outliers. Okay, when you have outliers, remember the squared error metric punishes large errors a lot, and so having outliers will significantly affect any kind of, I guess, training or model that you might fit if you're using squared error, mean squared error, or, you know, anything related to squared error as your metric of performance. And so this if you have outliers way out here, it's gonna affect how it gets fit. All right, so anyway, this is what we have. Median squared sale price was 160,000. The most expensive was 755,000. Yeah, if we use squared error to measure model performance, outliers can have a significant impact on our model. So to kind of help avoid that issue of using squared error being dramatically affected by outliers, one thing we can do is do a log transformation to the sale price. Okay, and what that does is it transforms everything. And so now this is our data. This is looking less skewed to the right. We have, now we have a tiny bit of skew over here, but generally I would say it looks better here. Okay, after we do a log transformation. And so so this is just doing a log transformation on the graph itself, not actually transforming the values. So if you actually want to transform the values, okay, you'd have to affect that, change that. So one thing we can do is we can take our Ames data set, and using kind of the tidyverse notation, we pipe Ames into the mutate function. And mutate, what mutate does is it creates new variables. And so we're going to basically create a variable sale price, and we're going to do a log transformation. We're going to use common log base 10. We're going to apply that function to the already existing variable sale price. So basically, when you do something like this with dplyr and use mutate, and you use kind of the variable name, and back here it's going to take this, do whatever you want to do with it, in this case apply the log transformation, and then it's going to overwrite the currently existing sale price column. Okay, you can give it a different name, but we'll just go ahead and take the log base 10 of sale price and replace our current sale price with that. Okay, normally when you take the data set and run it through mutate, it will return an entirely new data frame or tibble. But what we are doing is we're going to take that and we're going to store it using the arrow back into Ames. Okay, so if you're not familiar with the tidyverse notation, it feels a little bit strange seeing Ames, Ames arrowed back into Ames, and then there's this pipe operator. So basically, it's take the way R does the evaluation is it evaluates everything to the right of the assignment operator. Once it's all done, it takes the result and then it assigns it to this name Ames. What's to the right of the assignment operator? Well, we take the existing data set Ames and we pipe it into mutate, which means the way mutate operates is it takes a data set, so it might be like mutate Ames, takes a data set, and then it creates new variables. The new variable will be sale price, which is the name of an already existing variable. It'll replace that with the log transformation of that. So, so we'll go ahead and run that in R as well. So here, let me just show you what Ames mutate, and we're going to do sale price is equal to log base 10 sale price. Okay, and so what this will do is it will create an entire new data set. And what I want to do is I want to store this back into Ames. And so we'll see this column change. So when I do that, if I scroll over to the right to sale price, we can see sale price is now 5.33, 5.02. And so to kind of get back our original numbers, we have to do 10 to the 5.332438. And we can say, oh yeah, that was the 215,000. And then this one was 5.02, 1189. Okay, and that's 105,000 basically. And yeah, when you have log transformations, basically 5.02 and 5.33 are quite a bit different. Okay, going from 5 to 6 means the price went 10 times as big. And then if we do our ggplot here, now that sale price has been transformed, this is what it looks like. Okay, so we've done some just kind of very basics as far as introducing the housing data and doing a couple things, and I mostly just followed along the instructions given in chapter 4 here. There's a few more things that the authors of Tidy Modeling with R do in chapter 4. Let me make this a little bit bigger. Okay. So they do the log transformation. They also create this plot of the different neighborhoods. So one of the variables in the Ames housing data set is the neighborhood. Okay, and these are neighborhoods. Where did it go? Okay, I feel like all right. Well, I don't know where it is, but this is kind of a map of the city. This is not part of the data set. They call the different thing where they have the map drawn out, and but they plotted the coordinates, the latitude and longitude coordinates, and so there's different areas of Ames that have houses, and they plotted them, and you can see for the most part the different neighborhoods are separated out pretty well, and it's kind of tough to tell exactly which of these corresponds to which ones because you got these little dots and these little triangles, and they're all kind of similar colors, but overall the idea is basically when you look at one local area, is it just one color? And it seems like that's mostly the case. We have a couple weird things going on, right? There's like just a couple weird little pink dots here. It's a little strange. Within this neighborhood, there's like a couple green dots on the inside of this neighborhood, so I'm not quite sure what's going on. And then these dots out here, these are not really part of any neighborhood. So it's just like one individual house here or something like that. But, for the other things, like using the neighborhood probably gives you a sense of like, I imagine all of the houses in this neighborhood are kind of similar to each other, right? All of the houses in this neighborhood probably kind of similar to each other. The houses in this neighborhood probably sort of similar to each other. Of course, they're not going to be all the same. They're not necessarily like part of the same development or something, but they are geographically close to each other. And so that gives us that informs us a bit about the houses there, okay? So the authors kind of point this out, and they say, we have this one neighborhood, Timberland, I guess, is kind of geographically isolated from the others. I guess there's, they point this out. Meadow Village is like an island of properties inside the Mitchell neighborhood. And then there's some of these things. I guess this one was labeled incorrectly labeled. Some things are kind of isolated, and they kind of point all of these things out, just kind of seeing like, is this something we have to kind of worry about later? Because, when you're using variables, the idea is like you're hoping that variables providing information and having a little bit more insight into that variable, and knowing like, okay, it's going to provide information as long as it's not like one of these neighborhoods or something. That's going to help you in your analysis. All right. The next chapter in Tidy Modeling in R is titled Spending Our Data. But really, it's all about kind of splitting our data into training and testing data sets. Okay, so when we have our available data, okay, and we want to kind of create a model, there's a few things that we've got to do, right? So if we're taking a parametric approach, we have to kind of estimate our parameters for that model. We might have a non-parametric approach, and we probably just need a ton of data and things like that. But no matter what you do, you're probably going to try out more than one model, and so you have to select which model you're going to use at the end of the day. And then let's say you've selected a model. Another thing you need to do is tune that model, which means you have to kind of make some adjustments. So so for linear regression, the idea of estimating parameters is figuring out your slope parameters. Tuning the model would be along the lines of adding or taking away variables, choosing which variables to use. Other models that are different will have different kind of tuning steps. So for example, k nearest neighbors, a tuning step is how many neighbors do you use? Do you use 3 neighbors, 4 neighbors, 5 neighbors, 6 neighbors? Okay. Other kinds of models will have different hyperparameters to tune, all right, which will often determine like how many parameters need to be estimated, or how many, something like that. And then, and all of that is guided by our performance assessment. So we make some kind of adjustment. I say, instead of using k equal to 3, we're going to use k equal to 5. We need to assess, did things get better when I switched the number of neighbors from 3 to 5? Did they get worse? Did they stay about the same? So we need to be able to assess our performance. And all of these tasks require data, and you probably don't want to use the same exact set of data for doing every single one of these things, right? If you reuse the same data for all of the tasks, that's going to lead to problems. A lot of times you end up overfitting that particular set of data because it's the I guess it's the problem of using your data and assuming it's representative of the world. And so a silly example would be, let's say you meet a foreigner from another country, all right, and this is the only person you've ever met from that particular country, and that person says, oh, I'm used to doing things this way, okay? And now, based on your interactions with this one individual, now you assume every single person from that country kind of behaves the same way. And there might be some elements of truth to that, okay? But is it that everybody from that country behaves this way, or are you making assumptions about kind of just weird little quirks about this one particular individual, right? How do you know what applies to just this one individual versus the general population of that particular country? And similarly, when you have a set of data, are you modeling weird specifics of your particular set of data, or is this something that just generalizes to the population that this data represents? So to help us avoid that problem of overfitting, we have to kind of split our data into different parts, okay? And so kind of the most common way we're going to split our data is to create a training set and a testing set, okay? We have a training set and a testing set. Usually we give more data, around 80% or something around there, 75% to the training set. Okay, sometimes as high as 90%, 80%, 75, 80%, that's probably a good rough guide. But depending on how much data you have available, you can give even more or less to that training data. Okay, and then you use that training data to estimate your parameters, do any kind of feature engineering to try out different kind of models. And then when it comes to evaluating your performance, okay, then you switch over to the test set. Okay, the test set is kept separated, secret, apart from the model development process. Okay, and you only use that test set at the very end when you have maybe like one model or maybe two models, and you want to kind of have them compete against each other to help you decide which of these two is the best performing one. Okay, so the test set is then just used to measure the performance of the model, and you want to avoid using the test set over and over again. You really only want to use it once at the end. Otherwise, that test data set becomes part of the modeling process and you end up overfitting. Okay, you end up overfitting. So splitting your data into a training set and a test set used to be kind of a pain to do in R, especially if you cared about reproducibility. Like if you wanted somebody else to be able to do your thing and you wanted to split your data into a training set and a test set, it was it could have been kind of a pain, right? Tidy Models does this really nicely for us, and there's a function called initial split. Okay, so I'm going to go ahead and I'm going to run that right here. Okay, and then let me show you my environments pane. So right now I just have Ames, and I'm going to let's set the seed. Set seed 501. It's just an arbitrary number. What set seed does is whenever there's randomness involved in R, it's pseudo-random. It's not truly random. It's just following instructions in the computer, but they behave like random numbers. Okay, and set seed is basically if I set my seed and you set your seed to the same number, and we ask the computer for random numbers, both of our computers will generate the same set of random numbers. Okay, and here I'm going to call initial split, and we're going to do it on the Ames data set, and I'm going to specify how much do I want to go in the training set. So I'm going to say proportion 80%. All right, so I want 80% to go in the training set, the remaining 20% to go in the testing set. So I'm going to do initial split, okay, and we're going to do Ames proportion is equal to 0.8, and this will produce, oh, you know what, I need to save this as Ames split. We get a split object, okay, and what Ames split tells us is that it split the data. Okay, there's total of 2,930, so 2,930, if I multiply that by 0.8, I get 2344. Okay, so we can see 80% went into training, 586 goes into testing, and the remaining 2,009 for a total of 2,930, right? 2,344 in training, the remaining 586 into testing, for a total of 2,930 rows. Okay. And then if you want to work with that particular data frame, okay, you take your split and you call training on it. So I'm going to call Ames train. This is, I'm going to store this, and I'm going to call this function training on the Ames split. Okay, and what this will do is it creates that actual data frame. So you can now see if I ask for dim on Ames train, I get a data frame. I can say class Ames train, and it's going to basically be a data frame, a tibble technically, and these are all part of the tidyverse. But basically I get 2,344 rows, 74 observations. Okay, that's going to be the training, and then for the testing I do the same thing, but instead of training I call testing, and I'm going to store this into Ames test. Okay, and Ames test is the other 586 observations. Okay, I copied and pasted this directly from our textbook. Okay, and so when you do initial split, which is it's going to do simple random sampling to do this thing. And simple random sampling works a lot of the times. Okay, it says is appropriate in many cases, but there are exceptions. And there's a few things you should keep in mind, and you could get better performance if you don't do simple random sampling, but something like stratified sampling. Okay, so let's say you have a classification problem, and let's say you have a class imbalance. So your most balanced class would be something like 50% this and 50% that, and you just classify yes and no. But if you have something where one class occurs much less frequently than another, then you have class imbalance. So, if you use simple random sampling here, it says it may haphazardly allocate these infrequent samples disproportionately into the training or test set. To avoid this, stratified sampling can be used. The training test split is conducted separately within each class, and then these subsamples are combined into the overall training and test set. So let's say you are doing something on for a bank, and you're trying to figure out what percentage of customers are not going to pay their credit card bill and will default. Okay, and so when a customer defaults, basically now the bank has to try to chase down the customer to get their money back. Okay, otherwise, they might not get their money back. And so, but that might be a pretty rare. Maybe let's say 2% of the customers default. Okay, I don't know what the actual numbers are. All right, so you might have 1,000 customers in your data, and only 20 of them default. So you really want to be able to detect these customers well. Okay. Now technically, you can get 98% accuracy if you just assume no one's going to default, right? If you say, oh, no one's going to default, then you're going to be right 980 times out of 1,000. But that's not a very useful model. Okay. And if you do random, let's say you split this into a group of 800 and 200. Now, by random chance, it is possible that you don't get a perfect split here. Let's say you end up getting 7 people who defaulted in your group of 200. Well, 7 out of 200 is 3.5%. That's almost double what the overall percentage is, right? The overall percentage was 20 out of 1,000, around 2%. And if you get 7 out of 200, which is not an unusual thing to do when you do random sampling, now your percentage of default is 3.5%. Okay, so it's quite a bit different, and so that could lead to problems. So you want to do stratified sampling to avoid something like that. Okay. Similarly, for regression, regression is a little bit harder to stratify, but you would do something like you would create bins, maybe quartiles, and you have the top 25%, the next 25%, next 25%, next 25%, and then you do stratified sampling so that in the training data you have the same kind of group of 25% quartiles, and then the test data you have the same quartiles as well. Okay, and it says this is an effective method for keeping the distributions of the outcome similar between the training and test set. So if you wanted to do stratified sampling, okay, so here I have a numeric variable, sale price, and I can do stratified sampling just by kind of throwing in, so under initial split, proportion 80, I'm going to add strata equal to sale price. Sale price, is there a underscore in it? sale underscore capital P price. Okay, and then so now if I ask for Ames training and Ames testing, I can ask for dim on Ames training. I have to set the seed. Sorry. Let me just copy this. It's not copying. All right. Well. All right. So there we go. So so here it changes a little bit. Okay, 2342 is not exactly 80%. Okay, 80% was 2344, and we get something a little bit off. But this is going to help us preserve the proportions in our split, okay, to make sure we have the appropriate strata represented here. Okay. All right. Side note: if you are dealing with time series data, okay, when you do your train test split, you don't want a random selection, okay, of data. Basically, for time series, you generally want to predict something that's going to happen in the future. So you don't want. So let's say we have data up through today, okay, June. I guess at the time of recording, it's like June 25th, 2024. Let's say we have data up to this, and we want to be able to predict what's going to happen, the next day or the day after or something like that. Okay. You don't want to let's say we have years of data. You don't want to just say like, based on our thing, what happened, September 2023, September 5th, 2023, or August 8th, 2022, or something like that. That's not quite going to be useful. So what you want to see if your model is any good, you're going to say, let's pretend we have data up through May 2024, okay? And if we say the last day chunk of data is May 31st, 2024, how well does it then predict? I still have data up through June 25th, 2024. We can say, okay, how well does our model work going from ending, our training data ends May 31. We're going to test it to see how well it performs June 1st, June 2nd, June 3rd, June 4th of 2024 using the data up through May 31. Okay, and so in that case, you want your most recent observations as your test cases, and you can say, well, if it worked well for June 2024, then hopefully it will work well for July 2024 or something like that. Okay. So in that case, you'll use initial time split, and that will allocate, the first, say, 80% of the rows to the training data, and the last 20% will be the testing data. So far we've been doing training and test data, and what we said was that the test data should only be used once after we've narrowed everything down to maybe one or two final models. Okay, but before you get to the test data, you still need to be able to measure model performance in some way, because if you want to get it down to kind of your two finalists, well, how do you even measure that in the first place? Okay, I guess it's kind of like I don't know if these reality competition shows are still in the air, but there used to, like American Idol or something, you have the judges would evaluate and say, all right, these ones are going to the finals or something, and then once you get to the finals, then I guess the audience and the public will call in and vote and things like that. So the test set would be kind of like the audience calling in to do the final evaluations, but you need a way to kind of evaluate before you get to that test set. And so how do you do that? Well, we need a validation set, okay? So we have to further split the training data even further. And so the diagram comes from our textbook here, where it says spending our data, okay? And oh, is this not in here? Okay, well, I guess we'll do cross-validation. Okay, comparing models with resampling. Let's see if we have our... Sorry, I'm clicking the wrong... Oh, okay, so this is where we're going. Okay, we're going to do cross-validation. So we're going to split our data. We have all of our data. We do our initial split into training data and testing data. The testing comes in at the very, very end. But with our training data, we're further going to split that into basically an analysis set or an assessment set. Okay, but we're going to do this via resampling. We're going to do this using cross-validation. Okay, and so how does cross-validation work? Well, in cross-validation, we split the data into kind of random blocks, and each block will get to serve as the validation set at some point. Okay, so let me review this slide. All right, so it says cross-validation is a method that further splits the training data. Okay, so here's our diagram. Remember, we did our initial split into training and testing, right? And we use this at the very end. But now we're here. We take our training data. We're going to further split this up. Okay, we're going to further split this up into an analysis set and a validation set. Okay, now I could just also split it, but we want to do it a little bit better. Okay, the training and analysis set is going to be used to estimate the model parameters. And then we have the validation or assessment set, okay? And that's used to measure or evaluate the models and their performance before we reach the final stage. So here, if we have, let's say, n observations, okay? We're going to put some in the training set. And so this one happens to put observation 7, 22, 13, just kind of randomly ordered in there. And then we put the rest in the validation set, okay? This contains observation 91, any other observations, however it is. And then we fit data onto this, and we evaluate its performance on this. That would just be kind of randomized, a randomized example there, okay? In the ISLR textbook, they use the auto data set. Again, auto data set contains information about cars, and we're trying to, and in the example we're going to look at, we want to fit something about the relationship between the vehicle's mileage, miles per gallon, okay, and the horsepower. So higher MPG means that the car is more fuel efficient, and horsepower is a measure of like how much power the car has, how fast can it accelerate and stuff. We can try fitting a straight line linear model, but if we do that, it seems like we're not doing a good job. It seems like it's missing some important aspects. Whereas fitting a quadratic model where there's a little bit of curvature seems to do better, okay? And we could try even fitting higher degree polynomials, and that's going to further improve our performance on the training data, okay? We're going to get less error in the training data, okay? But we know if we just make our model too complicated, we'll run into problems, okay? So rather than looking just at the mean squared error in the training data, we use the validation data set. Okay, and so this is the this diagram here says how does our mean squared error change on the validation set. Okay, so we took our data and we split it randomly into training data and testing or validation data, and we fit, a linear model or a quadratic model or a third degree polynomial or whatever to this data, and then we're going to measure how well did it perform on the validation set. And so we can see when we went from a linear to a quadratic, we got a huge drop. When we went from quadratic to third degree or fourth degree or fifth degree, the mean squared error actually going from a second order polynomial to a third order polynomial, actually the mean squared error went up. And to the fourth order it went up a little bit, fifth order went down, so on and so forth. We're not getting that much drastic more improvement. It does seem like going from 5 to 6 to 7 to 8 even improves our performance a little bit, and maybe after 8, 9, 10 it just seems kind of flat. Okay, that's what we see for this. Okay, what does the graph on the right? So this indicates to us that, yeah, going from a linear to a quadratic model seems to improve things. Going from second order to something higher doesn't seem to make a huge difference. But that was for this particular randomization where, these observations ended up in my training data and this ended up in my validation set. If I had rolled the dice a little bit differently, if I did randomization on another day, I would get different observations over here, and then I would get different observations over here. And this graph over here shows basically the same graph, but what if I had a different randomization? Okay, so across the board we see going from 1 degree to 2 degrees improves performance, but in some cases much more dramatic, right? It went from here all the way down to here for this dark brown line, but it started off pretty bad and it got better, but it's still one of the worst performing models, versus this purple line dropped down here and it got pretty low. Okay, so again, a lot depends on just what random observations ended up somewhere and somewhere in one set versus the other. Okay, and but it's not consistent. Look, this line out here, going from 1 to 2, it resulted in improvement. Going from 2 to 3 to 4, not so much. It actually goes up. But going from 4 to 6 to 7, we see quite a bit of improvement for this particular line. Okay, but for this line right next to it, going from 4 to 7, it goes down and up and down because of just the random data points. We're getting kind of a different line. Here's another line. All of these are different lines, and so so we see that when we do the randomization for who's ending up in the training and who ends up in the validation set, the randomization part plays kind of a big deal. It's kind of a big deal here, and so do we just have to do it a whole bunch of times to kind of get an overall picture? Because if you only do it once, you might get this line. You might get any one of these lines. And if you only had looked at one line, you're hoping, well, I hope I got a good line. But there's no guarantee that you got a well-representative line, okay? So, so you just kind of want to make sure, you're going to make a good decision. So either you have to kind of repeat the process multiple times, and we can do that with something like k-fold cross-validation. All right, so here I wrote drawbacks of using only one validation set. Okay, so as we saw in these kind of previous graphs, the estimate of the test error can be highly variable depending on which random data points were selected to be in the validation set. Okay, only the observations in the training data are used to fit the model. All the observations in the validation set are not used. Okay, so that's also a drawback, because you're leaving out quite a bit of information when it goes far as training goes. All right, so the model's trained on even fewer observations, and so the performance can't be expected to be super great. Okay, so using a single validation set often overestimates the test error. So that's something we got to worry about. Okay. So there's a few strategies, and we can do something called cross-validation. And in cross-validation, we're going to split the data into two parts, but we're going to kind of reuse our data multiple times. So one of the simplest cross-validation approaches is leave one out cross-validation. It is simple in concept, but computationally it is expensive. So leave one out cross-validation involves splitting the data into two parts. Basically, the two parts is one observation that we leave out, and then the other part is everybody else. Okay, each observation or data will get left out at one point in time, and it will be served as the validation set. Okay, so it's kind of like every observation gets a turn to be, quote, it. Right? So if you imagine a game of tag or somebody who gets blindfolded and has to guess, everybody gets a turn at being that. Okay. Everyone else goes into the training set. All right, and we end up having to do this a whole bunch of times, n times. Okay, the model is fit on everyone else, and then now that we fit the whole model on everybody else, we say, okay, now make a prediction for this one guy over here. And so we calculate the difference between the actual value and our prediction, and then we do this for every single observation. We say, okay, we left out person A, person number 1 gets left out. We train on everybody else, person 2 through 100, 99. Okay, the 99 other people, 2 through 100. And then we say, okay, now that we have a model, let's predict person number 1. We write that down. Then we leave person number 2 out, and we train it on person 1, and then person 3 through 100. Okay, the other 99 people. And then we make the predictions. We have to do this 100 times. And then we do the mean squared error, take the average. That's going to be leave one out cross-validation. So here we have observation 1 through n. The first time we leave out observation 1, then we leave out observation 2. Then we leave out observation 3, and we do this over and over and over until we reach the end. And finally, we left out observation n. So this requires n splits. If you have a huge data set like 1 million observations, oh my goodness, this will take a very long time because you have to do this 1 million times, one for every observation. So that's a bit of a pain. That can be a bit of a pain. So an advantage, okay, the fitted models use almost the entire data set every single time, n minus 1 observation points. And so you get a pretty good sense of the test error. There's no randomness at play in leave one out cross-validation. Everybody gets a turn. The disadvantage, it can be very computationally expensive. It could require your computer to do a lot of calculations, especially if your data set is large. And this is a quote from our book. It says, leave one out methods are deficient compared to almost any other method. All right. For anything but pathologically small samples, leave one out is computationally excessive, and it may not even have good statistical properties. The R sample package does contain leave one out cross-validation as a function. These objects are not generally integrated into the broader tidy model frameworks, and that's fine. Okay, so it's there kind of as a thought experiment of like what would happen if you did this one at a time, but generally we don't do that. Okay. The better approach is k-fold cross-validation. In tidy models, it's called v-fold cross-validation, but it's the same exact concept. Okay, what we do is we take the data and we split it into k different groups, k folds, okay, of approximately the same size. The first, when we do this, basically, so here's 5-fold cross-validation. We randomize the order, and we do kind of 20% becomes our validation set. The other 80% is training. Here, the next 20% is our validation set, and we take the other in blue is the 80%. It's just like group 1 and groups 3, 4, and 5. Okay, and then we do another 20% for the third fold. This, the other parts are the training set. This one's the validation set for that one and that one. Okay, so that's how it goes. This has actually, in my opinion, a better picture. So we resample this. I don't know. Here we have, well, I guess B or 5 times or whatever, and we resample it, the analysis and the assessment set. How do we do that? So here, this is what 3-fold cross-validation looks like. So they shuffled it up and they said 1/3 of the data, it will be green circles, 1/3 of the data will be yellow squares, and 1/3 of the data will be blue pentagons. Okay, and for each fold, that one of those portions, so in 3-fold cross-validation, 1/3 is used as the validation set, and the other 2/3 are used for training to fit the models. The model is fit on these 2/3 and evaluated on this third. Here, the model is fit on these 2/3 and evaluated on the yellow squares, and the model is fit on the yellow squares and green circles and fit on the blue pentagons. Okay, so this would be 3-fold cross-validation. Heard that. Okay. Keep yawning here. And okay, so we calculate the mean squared error on the validation set, and we repeat this for each of the different folds. And the cross-validation error is found by taking the average of the mean squared error values. What kind of K do we use? I don't know. Often we do 5, sometimes 10, sometimes any number in between. There's no real rule. Not too many, but 5 to 10 seems to be popular choice here. Okay. What are the effects of changing V? This is coming from Tidy Models in R. It says larger values result in resampling estimates with small bias but substantial variance. Smaller values of V have large bias but lower variance. And here it says we prefer 10-fold cross-validation since noise is reduced by replication, but bias is not. I don't know, 10-fold. I would say 5 to 10. So this is 5-fold cross-validation, the idea there. Okay, and so here, this is the diagram of what is mean squared error when you do leave one out cross-validation. There's no randomness when you do leave one out cross-validation because every single observation is used as the validation set. So this is the exact path that happens when you do leave one out cross-validation. You fit a linear model, then a quadratic model, and we have a dramatic drop in mean squared error. Then 3rd degree, 4th order, 5th, 6th, 7th, 8th, 9th, up to 10th order polynomial. And it seems fairly flat, little bumps ups and downs. Okay, 10-fold cross-validation. We have something very similar, but so we going from 1 to 2. All of these almost line up perfectly, exactly the same. But here, as we go from 2 to 10, we see the different colors of lines, which indicates these lines aren't all following the exact same path. There's a little bit of variation from one line to another, and that's because there is randomness, right? In this thing, who is a green circle or yellow square or blue pentagon is a random selection. And so if we ran it again with a different set seed, random seed, we would probably get different assignments. And then our model performance would be just ever so slightly different, okay? Not dramatically different, but yes, a little bit of difference. And so that's why we're seeing a little bit of variation here. Not dramatic variation, but definitely there's a little bit of variation. And so, one on the left, there's no randomness, okay, but the one on the right shows a little bit of variation, but only a little, okay. So technically, leave one out cross-validation is just a special case of k-fold cross-validation where the number of folds is equal to your number of observations n. Again, not the best idea. Doing k-fold cross-validation, it's going to reduce that computational expense by fitting only k different fits. So the idea being k is only 5 or 10 or something like that, and much less computationally expensive. So save some computational power. With the cross-validation, we have a couple purposes. One is it can be used to estimate the mean squared error of the test data itself, right? And it can also be used to figure out kind of the location of the MSE of the test data. So, and that's going to help us decide which set of model parameters will end up leading to the lowest test case mean squared error. So, we're doing everything on the training data, but we're trying to estimate stuff about the test data. Okay, so how do we use cross-validation to estimate the mean squared error of the test data? That's kind of tricky, right? Because exactly, we don't really know exactly how much mean squared error there is in the test data, because we don't really know the exact model that exists in the population. Okay, but what we can do is we can kind of play around with this thought experiment where we can say, what if we simulate the model ourselves? And if we do that, because we are generating the data, we can say we can specify the model so that it produces a certain amount of mean squared error. Okay, we can say we know exactly what numbers we put into the simulation, so we know the mean squared error should be right around here. And then what we'll do is we'll kind of revisit the different models that we had back in chapter 2 when we were talking about the difference between basically bias and variance, the trade-off between model flexibility and the resulting mean squared error. And if you remember that example, we had these different smoothing splines with different levels of flexibility. The least flexible model just fit a linear thing, and then most flexible ones, were wiggling around and were able to fit the training data perfectly. And, but having too flexible of a model and fitting the training data perfectly, we overfit it, okay? And it didn't work well for the test data. So when we do cross-validation, it's important to remember cross-validation is kind of like our workaround for not having access to the test data, okay? So cross-validation, you still don't have access to the test data, but what we're doing is we're kind of simulating it by artificially disabling the data that we can look at, right? So we divide our available data into, training and validation, and we can kind of try to estimate what the mean squared error is, right? And so, we saw these graphs, right? And the idea being, the red graph shows the true mean squared error, this dotted line, okay? And we see that as the model flexibility increased, the true test mean squared error dropped down, but then started climbing back up, okay? And we know this line only because we simulated the data ourselves, right? Only because we simulated it. Normally this is not known to us. Okay, same kind of idea here. We're able to look at this red line and we can say, okay, we know what the mean squared error should be, and we can kind of calculate, how well do these different models fit. And when you have one that's too flexible, the mean squared error on that thing is too high. Okay, and we saw this thing with the linear thing. So we drew these because we know exactly how the simulated data set, because we generated the simulated data set ourselves. Okay, these plots, okay, show us how good our estimates will be. So the blue line is the true mean squared error from our simulated models. Okay, and again, we only know this blue line, the true mean squared error line, because we simulated the data ourselves. Here is if you tried to estimate the mean squared error using, let's say, leave one out cross-validation or k-fold cross-validation, this would be the curve that you get. The black dotted line or the orange line, which are very similar, is based on how much mean squared error do you estimate based on k-fold cross-validation. Okay, and so here we see, these things have the overall shape of the true line, which is shown in blue, but it's not a perfect match. Okay, so here, we're trying to estimate the mean squared error of the test data based on k-fold cross-validation. We get something kind of close, but not perfectly. More importantly, are we going to pick the right model with the right amount of flexibility? Okay, and so we see, we get kind of close. So because we know the answer, we can say, okay, the correct model had something around flexibility level 5, and we're guessing probably a flexibility level of like 9. Okay, looking at the graph here. So we're off by a little bit, but we're not picking something overly flexible, and we're not picking something super inflexible either. So we're kind of in the same vicinity. Something over here, we know the answer in blue, our estimated values in this dotted line and orange line. Similar, overall shape similar, but the exact path it took a little bit off. And here we're probably overestimating the amount of flexibility we should have. We're estimating something around 5, where the true value is probably something around 3. Okay, and here's again similar shape, especially once we get to a certain amount of flexibility. Very, very similar in terms of the red, orange and black dotted line and the blue line. They line up almost perfectly, and we can see, okay, the true value is right around 10, and we're estimating something very close to that. Okay, a little bit higher, a little bit lower. So estimating the test mean squared error, we didn't do a perfect job, but also not terrible considering the fact that we never saw the test data. Okay, we never saw the test data. We're just estimating on the random training data that we have. Okay, again, we can estimate the test error ourselves, and we can try to estimate the best location. So I said, the previous graph showed that estimating the amount of test mean squared error may not always prove accurate results. These lines don't have perfect harmony or match. Okay, but the location of where the test MSE is minimized and identifying that goes pretty good. Okay, goes pretty well. The goal was trying to figure out how flexible our model should be, and I think overall, if we used the estimated mean squared error from leave one out cross-validation or k-fold cross-validation, we would have gotten it right, or at least ballparked it fairly well. Okay. All right. How do we do cross-validation in tidy models? So for us, there is a function called v-fold cross-validation. And so what we're going to do, so remember, we've already done the initial split. We've already done the initial split, and where we split training and testing. And so what we're going to do is, now that we have the training data, we're going to do v-fold cross-validation on the training data. So remember, in R, I went from Ames, I created a split, and now I have, and then I took the split and I created Ames test and Ames train. So I'm going to take Ames train and I'm going to apply v-fold cross-validation to that. All right, here we're going to we'll set our seed. My seed will be set seed 1001, just some arbitrary numbers. We'll set that, okay? And then we're going to do aims folds. We're going to create a new object, and this is going to be the result of vfold cross-validation. We're going to do it on the training data, not the full data, not all of aims, but the aims training data, 2,342, and we're going to say v equal to 10. We want 10 folds. V equal to 10. Okay, so that's done. We have aims fold, 10 observations, it's 10 folds. So what is that? Aims folds, these are my 10 splits. And so if you think about 2,342 observations and you divide it into 10 groups, okay, you're going to get basically 10 groups of 234. You have 2 left over, so you'll have 2 groups of 235. So you have 8 groups of 234 and 2 groups of 235. And so we have our 10 splits, and we can see what we have. We have the first split, 2,107 in the assessment, 235 in the validation, or 2107 in the training or assessment, and 235 in the validation, and so on and so forth. So this is how the different folds work out or get applied there. So you can take a closer look by calling aims underscore folds $ splits. Okay, so if I do aims fold splits, okay, so here we get a list, and we can see, okay, the first thing in the list is we have a whole bunch of basically train test splits, or analysis, assessments, and totals. So I can ask, there's a structure on this. Oh dear, it's a little bit too much. Okay, well, so we can see, all right, if I square bracket 1, okay, so this is very similar to, say, like an aims split. Okay, where you have training, testing, total. Here you have analysis, assessment, and total. And if you wanted to, you could, out of that, you could get those particular 2,107 particular observations there. Okay, and so here, if I call analysis on that, okay, aims fold splits double square bracket 1, and I call analysis, I will get the 2,107 rows. And I can call assessment, and I will get the 235 rows that are in the assessment set. Okay, now we wouldn't use this directly. This was all part of the pipelines that we would use as far as what do you call it? Tidy models goes. So as far as tidy models goes, it's all part of the pipeline. But you could, if you wanted to look at this 2,107 and these 235, you could. That option is available using analysis and assessment. But we're not really going to do that. Okay. Instead, we're going to kind of pair this thing up with, say, something like package tune, which is going to run through this entire vfold cross-validation. And Tidy Models is smart enough to know how to handle this. Okay, so we just give it instructions to say, hey, we want to do vfold cross-validation, and then Tidy Models will understand, oh, okay, this is vfold cross-validation, so then when you fit this model, it's going to know that what it has to do is it's going to fit the model 10 times. Okay, it's going to first fit it on these 2107 and then evaluate on these 235. Then it's going to fit on this 2107 and evaluate on that 235. So Tidy Models is smart enough to know what it's supposed to do with this vfold cross-validation object. Okay. You could, because there's randomness involved, you could do multiple cross-validation, right? So, yeah, one issue with cross-validation is that the model performance does vary from kind of one set of folds to another. So you can do it even more times. So you can do 10-fold cross-validation repeated 5 different times, and you call v-fold cross-validation v equals 10, repeats equals 5. So I'm going to create this thing, repeats. So this will be rep is going to be repeated Ames folds. Okay, I'm going to do v-fold cross-validation on the training data, 10 folds, repeat it 5 times. When I do this, this is basically 10-fold cross-validation, but it's going to say repeated 5 times. So it's doing the splits and it's thinking about it. I'm not sure what happened. Okay, it got stuck, but you're going to basically get this thing: 10-fold cross-validation repeated 5 times. Here I get repeat 1, and then we'll have 10 folds, and then we'll also see repeat 2. Okay, here we go. Repeated 50 observations of 3 variables. I want this, but I want to print and do n equal to 30, 35. Okay, so here you can see repeat 1, and we have 10 folds on repeat 1 here, and then I got another 10 folds on repeat 2, and then I have another 10 folds on repeat 3, and so on and so forth. Okay, so it repeated it 5 times, so we're going to end up getting kind of 50 of these splits between training and assessment. And so that you can do v-fold cross-validation like that. Okay. There's even more. So if you look at, say, chapter 10 in our textbook, so this is the resampling methods where we have cross-validation, but there's even more that you can talk about. So this is repeated cross-validation. I guess we have Monte Carlo cross-validation. It says another variant of v-fold cross-validation is Monte Carlo cross-validation. And so like v-fold cross-validation, it allocates a fixed proportion of the data to the assessment sets. The difference between Monte Carlo cross-validation and regular cross-validation is that for Monte Carlo cross-validation, this proportion of the data is randomly selected each time. So this results in assessments that are not mutually exclusive. Okay, so here, here you say, like, I want 10% of my data to be in my evaluation set. So the diagram that we had earlier, for v-fold cross-validation is we have 20%, 20%, but all of these, the 5 different folds are mutually exclusive, right? So basically, out of your entire data set, if you have, say, so in our thing, we had 2,342 observations in the training data. We split it, so we had basically 10 groups of 234, or 8 groups of 234 and 2 groups of 235. But basically, each observation, every observation one at a time, gets to be part of the validation set. And we kind of split it up that way. Monte Carlo cross-validation just randomly selects and just says, oh, we're just going to get 10%. So sometimes some observations get picked more than once, or a bunch of times, and other observations don't get picked at all, and that could happen that way. Okay, so that could happen. And it says, oh, I guess you can do also bootstrapping, rolling forecast. Rolling forecast would be for like time series stuff. So you have some of these options. So validation sets, training, validation, testing. This is generally how it works. But here we do resampling and bootstrapping. This is just some other techniques, but I don't think we need to get into it right now. Okay, so it says I won't test you on this. Actually, I'm not going to test you on anything. You're just doing a final project. Okay, and then again, we're getting a little bit of ahead of ourselves because I haven't even covered how to fit a model. But let's say we have fit a model. How do we then evaluate the performance of the model? Okay, so what we're going to do is we're going to create something called a model workflow. And this is basically how you set up your model. Okay, and then once you have your model set up, then you evaluate it by calling fit resamples. You fit that model basically on the different folded resampled data. Okay, so we have the data and it's been resampled to form these folds, and you basically take the model and you fit it to the folded data, right? So we have our folded data, so either repeated Ames folds or Ames folds, which is basically the training data kind of folded up in these different ways, where we have 10 different splits of the train test thing. And then when you do that, when you call fit resamples on that, then again, Tidy Models is smart enough to say, all right, I'm going to fit it on this training set. I'm going to evaluate it on the validation set. And it does it over and over and over again. Okay. So fit resamples will fit the model you specified to all 10 folds of the data automatically. For each fold, it will calculate and produce several objects that will be of great use. It will calculate the metrics, and it will calculate predictions. Okay, it will calculate things like the root mean squared error for the different folds of the data. It can summarize and average all of these things together, or you could actually look up the individual metric for this one particular fold if you wanted to. Okay, generally you just want it to get you just want an overall number, so you'll just call something like collect metrics. Okay. Similarly, you can also say, all right, well, what kind of predictions should we get for everything? And you can call fit resamples, and it will create the predictions, and we'll collect the predictions. Okay, that's it for this. Just kind of introducing cross-validation, just because that's going to be an important concept as far as evaluating and helping us select the right kind of model. And again, at the very end, we will evaluate everything on the test data. But I guess, looking ahead to our final project, I will do the initial split between training and testing. Okay, and so like in the Kaggle project, I have like the master copy of all the data, and I'm going to do the initial split between training and testing. And the testing data will go onto Kaggle, and this is how we're going to measure the group's performances against each other, your group versus another group versus someone else's group. That's going to get put on the testing data. I'm going to release the training data to you guys. So then how do you pick your model? Well, you're going to split your training data into, doing something like v-fold cross-validation. and do this analysis and assessment. Okay. If you want to take your training data and then treat it like it was all the data and do initial like a initial training testing split onto that's fine. That's up to you. But yeah, basically there will be like a secret test set for each competition on Kaggle, and that's how we're going to evaluate the performance of everybody. All right, but we'll wrap things up here, and we'll see you next week.